distinguished guests, partners, members of the media, ladies and gentlemen, good morning and welcome. My name is Hamda Al-Hosani, a researcher at the National Center of Meteorology, and it's my great honor to moderate today's press conference. Thank you all for joining us on this important occasion as we officially announce the winners of the sixth cycle of the UAE Research Program for Rain Enhancement Science, managed by the National Center of Meteorology. Before we begin, let me briefly walk you through today's agenda. We will start with a short video highlighting UAEREP's journey, its past, present, and future. This will be followed by an opening remarks from His Excellency Dr. Abdullah Al-Mandous, President of the World Meteorological Organization and Director General of the National Center of Meteorology, and Ms. Alia Al-Mazroui, Director of UAEREP and Director of the Research and Weather Enhancement Department at the NCM. Following the speeches, we will move into the awardee technical presentations, where the newly selected awardees will share insights into their winning projects. After the presentations, we will open the floor for the Q&A session from our media colleagues with the UAEREP and the NCM leadership as well as the awardees. We kindly ask our media colleagues to introduce themselves and their organization before asking a question. And finally, we will conclude with one-on-one media interviews in the press room, followed by lunch. With that, let us begin. Please join me in watching a short video that captures UAEREP's 10-year achievements, its current impact, and future ambitions.
In the heart of the arid desert, water scarcity was a daily challenge and a symbol of resilience. Across dry regions worldwide, climate pressure and rising demand strain water security. In the United Arab Emirates, this challenge was met with a clear vision. The UAE Research Program for Rain Enhancement Science was established, not as a single project, but as a global research platform, pioneering rain enhancement research through validation, innovation, and international partnership. Over the past decade, UAEREP has supported research across continents, connecting scientists, institutions, and disciplines through sustained investment and rigorous evaluation. Ideas evolved into practical solutions. Today, UAEREP stands as a globally respected research ecosystem, strengthening knowledge, improving precision, and complementing existing water solutions. As it enters its next decade, the focus remains clear, from discovery to impact. Because securing water for the future requires commitment to science and the discipline to keep advancing it.
Thank you for your attention. Ladies and gentlemen, it's now my great pleasure to invite His Excellency Dr. Abdullah Al-Mandous, President of the World Meteorological Organization and Director General of the National Center of Meteorology to deliver the opening remarks.
Shukran Hamda, thank you. Bismillah ar-Rahman ar-Rahim. Your Excellencies, media representative, ladies and gentlemen, Assalamu alaikum wa rahmatullahi wa barakatuh. It is an honor to welcome you today as we announce the awardees of the sixth cycle of the United Arab Emirates Research for Rain Enhancement Science. The event today marks a turning point for global water security driven by science, innovation, and our shared commitment. I would like to begin by expressing our sincere appreciation to His Highness Sheikh Mansour bin Zayed Al Nahyan, Vice President, Deputy Prime Minister, and Chairman of the Presidential Court, for his continued support for the UAE Rain Enhancement Program since its launch in 2015. Under his guidance, the program has become a leading global hub for scientific collaboration and having top researchers and institutions all over the world. By investing wisely, we turn bold idea into a practical and sustainable solutions. Over its past cycles, we have built a world-class foundation for scientific excellence by supporting cutting-edge research and global knowledge sharing. We are not just following trends, we are setting them. Dear participants, our platform is open to collective and built on a track record of success, strengthening our economy. Let us now turn to the power of AI. AI is no longer just a tool, it is the operating system for how we solve the world's most complex challenges. It has completely redefined what is possible for global water security. Today, newly awarded projects will accelerate the mission by integrating AI, advancing radar, and nanotechnology. We are developing the next generation of solutions to make rain enhancement more efficient and sustainable than ever before. We are turning our vision into reality by making the UAE the global home for rain enhancement, where the world's best ideas are explored, tested, and put in a place for a global water scarcity. Dear scientists and participants, the UAE chooses act over words. We are a nation focused on a long-term innovation and building deep roots with the global scientific community. I extend my sincere congratulations to the awardees of this cycle. I am confident that your research will deliver breakthrough to water scarcity, and your success strengthening the UAE role as a leader in the sustainability, and we are proud to provide the ecosystem where your ideas can thrive. Thank you to all researchers and institutions who joined this cycle. Your expertise is the heartbeat of our mission. Together, we are securing water for the future generation. Thank you very much. Thank you.
Thank you, Your Excellency, for those insightful and inspiring remarks. As highlighted by His Excellency, today marks yet another milestone in UAEREP's leadership in advancing rain enhancement science, addressing one of the most pressing global challenges, which is water scarcity. UAEREP continues to foster innovation and scientific excellence, strengthening its role as a global hub for research, development, and deployment of rain enhancement technologies. At this point, I'm pleased to invite Ms. Alia Al-Mazrou'i, Director of UAEREP and Director of Research and Weather Enhancement Department at the NCM, to share her insights into the UAEREP's journey and to announce the winners of the 6th cycle.
Thank you so much, Hamda. Your Excellencies, distinguished partners, media representatives, ladies and gentlemen. Assalamu alaikum. It is my great pleasure to welcome you all to this press conference announcing the awardees of the 6th cycle of the UAE Research Program for Rain Enhancement Science, UAEREP. I extend my deepest gratitude to His Highness Sheikh Mansour bin Zayed Al Nahyan, Vice President of the UAE, Deputy Prime Minister, and Chairman of the Presidential Court, for his unwavering support for UAEREP's efforts to develop practical, science-based solutions to address water security challenges both for our nation and for the world. This support reflects the vision of our leadership to ensure the sustainability of water resources for future generations by prioritizing innovation, scientific excellence, and the development of national capabilities. As a nation that plans with patience and acts with insight and discipline, this reflects the UAE's wider belief that progress is firmly cemented in prudent ambition and innovation. Ladies and gentlemen, water security remains one of the most pressing global challenges, especially in light of accelerating climate change. According to the World Meteorological Organization's State of the Global Climate Update, 2025 is said to be one of the warmest years ever recorded, capping the hottest 11-year stretch in history. For arid and semi-arid regions like ours, this reality underscores the urgency of securing sustainable water supplies amid rising population and increasing environmental pressures. The UAE recognized this challenge early on and took bold, proactive steps to mitigate this impact. With annual rainfall averaging less than 100 millimeter, high evaporation rates, and limited groundwater recharge, innovative solutions are not a choice, they are a necessity. The nation has made a conscious effort to be a nation of both action and substance. Under the umbrella of the National Center of Meteorology, UAEREP continues to support the global scientific community in developing advanced, scalable, and sustainable solutions. We practice what we preach, real and radical collaboration, forming bonds out of conviction, consistency, and strength. Our program plays a vital role in reducing reliance on traditional water sources and strengthening resilience against climate change impacts, positioning the UAE as a leader in scientific innovation for water sustainability. Because sustainable progress is about designing a better engine that works for all, ignoring the constraints and delivering change and scientific innovation. Since its inception, the program has allocated nearly $25 million in R&D investments, secured 10 patents, and supported pioneering projects that have advanced rain enhancement science on a global scale. The program's efforts have earned several international recognition achievements, affirming its role as a catalyst for innovation and sustainability. This emphasizes the program's dedication to advancing collaborative research, establishing strong partnerships with leading research institutions worldwide, and creating a cohesive ecosystem of knowledge exchange and technological advancement. To this end, we say to the scientific community that we are open for collaboration and partnership as we all look towards an innovative future in water sustainability. Today, we celebrate the awardees of UAEREP's sixth cycle, whose proposals exemplify the highest standards of scientific innovation and practical application. Notably, across industries and sectors, artificial intelligence is transforming the way we all work. For the first time in history, AI is becoming embedded in everything we do, and it has become integral to our approach in addressing water security challenges. And the program awardees are example of this approach, one that is being adopted across the UAE and beyond. So, the three awardees are Dr. Michael Dixon, a principal radar meteorologist and software engineer at EcoScience, works in Boulder, Colorado, in the United States of America. Awarded for his proposal, Advancing Cloud Seeding Science and with Dual Polarization Radar Signatures and AI. Dr. Linda Zhu, an adjunct professor at the Institute of Sustainable Industries and Livable Cities at Victoria University in Australia. Awarded for her proposal, AI-assisted development and optimization of glaciogenic cloud seeding materials. Dr. Oliver Branch. A senior scientist and head coordinator of the Land Atmosphere Feedback Observatory at the Institute of Physics and Meteorology at the University of Hohenheim in Germany, awarded for his proposal, Rainfall Enhancement through Modification of Land Cover and Landform Rainland. We congratulate you on this outstanding achievement and look forward to seeing your research deliver impactful solutions that benefit communities worldwide. You will benefit from the program's accumulated knowledge, technical resources, and extensive global network to achieve your project's objectives. The UAE offers what partners value the most: the stability, the leadership, and the long-term vision to achieve your goals. This support will transform your ideas into practical solutions that deliver measurable impact and strengthen global efforts in water security and climate resilience. Your work represents hope and progress. We are proud to stand with you as partners in this journey. Together, we will continue to push the boundaries of science and technology to create a future where water security is not just an aspiration, but a reality. In closing, I extend my sincere appreciation to all our partners, collaborators, supporters. Your dedication and commitment empower us to lead transformative ideas and turn them into real-world solutions. Let us continue working together with passion, commitment, and determination toward a future where sustainable water security is achieved for all. Thank you all for joining us today.
Thank you, Ms. Alia, for your valuable perspective and for announcing our new awardees. To all the winners, congratulations. Your project proposals hold immense promise in shaping the future of rain enhancement science and advancing UAEREP's mission to develop next-generation solutions for sustainable water security worldwide. Now, let me invite our awardees to the stage to present their technical presentation. And each awardee will have 10 minutes to present their project, and we kindly ask our audience to please save any questions until all 3 awardees have completed their presentations, as we will have a dedicated Q&A session following the technical presentations. So let us begin. First, I'm pleased to invite Dr. Michael Dixon, Principal Radar Meteorologist and Software Engineer at EcoScience Works in Boulder, Colorado, USA, to present his project titled Advancing Cloud Seeding Science with Dual Polarization Radar Signatures in the Eye.
Good morning. So our project, as you can see, is aimed at. Oops. How do I do this? There we go. You can just use the. Okay, thanks. Thank you. So we're aiming to upgrade effectively some quite legacy systems into the modern era with dual polarization radar, taking advantage of what's available in the UAE now, using AI to help with that effort, and then providing a modern dashboard interface for seeding operations and capacity building to provide a pipeline of qualified personnel who can then operate this system into the future. So the UAE has spent a considerable amount of investment on modeling and observational systems. They have a dual polarization radar network now, which can observe the storms across the country that are involved in seeding, and there is a real-time data telemetry system to get aircraft data back to the ground in real time. So what does a storm look like on radar? Conventionally, this is more the old style. This is radar reflectivity of a thunderstorm. On the left there, you'll see the plan view looking from on top, and on the right, you'll see a slice through a thunderstorm. And this reflectivity field gives you an idea of how powerful a storm is, what the, how big it is and how strong it is, how, its size and so forth. But it doesn't tell you a lot about what's going on inside the storm. It doesn't give you clues about the microphysics. But if you incorporate dual polarization information into this slide, then you get something that looks like this. This is the particle ID, the type of hydrometeor that exists in that storm. And you can see now, instead of just reflectivity, we can see where we think there's hail or grauple, rain, ice, snow, or insects, because that also shows up on radar and so forth. So dual polarization really expands the information that's available through a radar observation, and that gives us much more information to make use of if we're going to incorporate AI into both operations and analysis. So the Titan system is our proven system that's been in operation for over 30 years. It's good, it's widely used, but it's still single polarization. It was developed previously to the rollout of dual polarization data across radar networks worldwide. So this is good, but out of date. If we incorporate dual polarization information, so on the right there, you'll see at the top, we have the 4 fields that we generally use to investigate or, try to evaluate seeding, and that's area, volume, and then a measure of the mass of the storm, or precipitation, which is dependent on single polarization, which is not very accurate. But if you include dual polarization fields, you get a lot more information like the rain fraction, the snow or ice fraction, and critically for a rainfall enhancement program, you get a qualitative precipitation estimate that's based on dual polarization data, which is much more reliable and much more accurate than conventional radars. So why AI in storm-based seeding operations? Well, for one thing, obviously AI has come a long way, and it's now incorporated, as has been said this morning, in a lot of our lives and so forth. We specifically plan to use AI in 3 ways: to correct systematic errors in the forecasting of storm position and size, to anticipate storm evolution windows relevant to seeding, like when is a storm available for seeding, or when is it likely to respond, and then for post-processing to try and analyze whether the storm reacted to seeding, whether there was a positive effect. And adding AI would not be very helpful if we didn't have the dual polarization information available. So it's the combination of the two that make this an attractive proposition. So in terms of the forecasting component for AI, this is already proven. Work has been done out in academia to show that with Titan, you can take storm tracks and correct for the biases. So this is not just a promise. This is something we know will work, but it hasn't been incorporated into operations. So, what we plan to do is move it from the academic side into an operational setting. Secondly, for predicting the seedability, we want, when you're operating an aircraft for seeding, you want to know which storms are most likely to respond to seeding. And we believe that using the dual pole features and AI, we can, as input, take things like, growth rates and various dual polarization signatures, put them into something like a short sequence temporal model, and then the output would be the probability of a storm entering what we call a seedability window within the next few scans. In other words, how likely is it to respond to seeding? And the outcome, would be also enhanced timing and targeting of seeding cases. And then for post-analysis, it's important that we evaluate how well we're doing in terms of seeding effectiveness. This is a difficult problem to cope with. Earlier in the history of this, we did things like randomized experiments, which we no longer can afford to do. But what we plan to do is use AI in its place and train it up on unseeded storms, look at what the typical evolution of storms is in terms of things like, rain mass and dual polarization microphysics, and then evaluate the trajectories of these properties for seeded storms and see if we can detect some difference between the seeded and unseeded pools using AI. Once again, that's an important aspect, is the fact that to do this manually would be very difficult. So in terms of expected outcomes, we're aiming for a fully operational dual polarization aware Titan system here at NCM. And we would have an AI-assisted nowcasting and seedability forecasting system to support the project in real time. For post-analysis, our AI system would help to evaluate whether seeding has been effective. We will provide an enhanced dashboard system that is dual pole aware, so that the operations can be carried out more effectively. And then finally, capacity building. We know that for a system like this, or for the project in general to be effective, you need expert people who are trained up and available. And so we plan to have a training program that helps to ensure that we have engineers and scientists available to staff the project in the long term. Thank you.
Thank you, Dr. Dixon. Next, I invite Dr. Linda Zhu, Adjunct Professor at the Institute for Sustainable Industries and Livable Cities, Victoria University, Australia, to present her project titled AI-Assisted Development and Optimization of Glaciogenic Cloud Seeding Materials.
I need to using the view, which is...
Oh, 1 second.
I think
This is not yours.
I need to using the view. So... Good morning, ladies and gentlemen. My project is AI-assisted developing and optimization of glaciogenic cloud seeding materials. The project team will be led by myself as principal investigator, and a number of other co-PIs will work collaboratively, include Dr. Otmar Möchler, Mr. Kurt Hebert, Mr. Kurt Hebert and Professor Hua Wang and Dr. Jianhua Zhang. So I will start from background information. So what is cloud seeding? It is a weather modification technique used to increase the precipitation either as rain or snow. So there are two types of cloud seeding processes. One is called hygroscopic seeding for warm cloud, where we're using the seeding agents to accelerate the water vapor condensation and form droplets through a process of collision coalescence. And the figure here shows a concept of a core shell structured seeding material developed in my first year project. And the second type of process is called glaciogenic cloud seeding process for cold cloud, where the ice crystals are formed and in the cold cloud where containing supercooled liquid water, where the fast growth of ice crystals leading the snow precipitation. So cloud seeding application actually can help and mitigate the climate change impact and also increase the water supply through increased rain precipitation, enhanced snow precipitation, heat wave suppression, and regional cooling, etc. The map shows the trend of snowpack in U.S. West States mountain areas. The red dot indicate a wide spread reduction in snowpacks in these areas over the past 75 years. Further, Nature Journal published a news article in 2015 that Californian snowpack reached lowest in past 500 years. And if you see the journal photo, you can see the snow barely covers the ground in the ski resort and the mountain peaks with very little snowpack coverage. So in this situation, the glaciogenic cloud seeding could play a positive role to enhance the snowpack, not only in this region, but also in any other regions in demand. So what is glaciogenic cloud seeding agents? So according to the physical chemistry of ice nucleation, when the water is with some impurities, it can form ice at much higher temperature. And such impurities are often insoluble particles, named as ice nucleation particles. And these ice nucleation particles has a similar crystal structure as the typical ice crystals, and that's how they work very well. The first research question of this new project is, are we using the most suitable seeding agents? And we will push the boundary of ice nucleation efficiency and searching for answers for the suitable ice nucleation agent. The second question is to be addressed by this project is how to generate reliable and sufficient experimental data sets which can derive statistically significant conclusion of the seeding effects, which is sort of missing at the moment. So AI will play an important role in this project. As in general speaking, AI algorithms and platforms can accelerate the examination of more variables and larger data sets to save time and cost and associated with endless experiments. So in this project, AI analysis, assisted analysis will be conducted on agents' property affecting ice nucleation performance, and also machine learning models will be developed, trained, and applied on the experimental data sets, help to extract the patterns and insights when we're comparing across the different INPs. Artificial neural network will be developed using the backpropagation algorithm in order to analyze the data sets and make predictions without experiments. So the hypothesis of this project is the high-performance, efficient ice nucleation agent can be identified and fabricated, and their performance can be optimized through the combined cloud chamber experiments and AI-assisted analysis and modeling. So a stage-wise approach will be used in this project. First stage will be developing the material. We will engage with the recently available AI platforms to search for the properties affecting the ice nucleation. The novelty of this approach is search AI platforms has an advanced AI function which enable taking search questions stepwise with logic and rationale, simulate human research assistant, however with much wider, deeper, complete coverage. And the second task will be design the material. And then we were using a range of available chemicals methods. And also we will synthesize and use the dimensional materials, such as 0 dimension, 1 dimension, 2 dimension, and 3 dimension. They all the possibility. The stage 2 of the project is portable cloud chamber evaluation and AI simulation. So Pine chamber has to be first set up, commissioned, and the operation will be trained. Then we will develop the experimental methods. The second task will be comparing different IMPs. The first IMP to be tested will be the silver iodide flare available commercially. We will combust it, take the aerosol sample, and feed into the Pine chamber. So the results obtained will be used to compare against different IMPs. The other material to be tested listed here, including new material to be developed. And the third task in this stage will be simulation and prediction by ANN models. Example shows a multi-layered structure of ANN network and a reiterative flow chart. The last stage of the project is scale-up feasibility and cost-benefit analysis. So the feasibility of the scale-up production will be evaluated. Two approach will be covered. One is bottom-up approach, another one is top-down approach. Bottom-up approach means you assemble the nanomaterials molecule by molecule using chemical method. And top-down approach means you work with the bulk material and using mechanical attrition like ball milling, mixing, lithography, etching, etc. And the last task will be cost-benefit analysis. The CBA will weigh out the raw material cost of this new material against its long-term benefits, such as enhanced performance in snow enhancement, and also energy efficiency, whether they need combustion or not, and of course the level of innovation. And the results will be derived into to reach the conclusion of cost-weighted final recommendations. That is a brief project introduction. Thank you for your attention.
Thank you, Dr. Linda. We now move to our third and last presentation. Please welcome Dr. Oliver Brandt, Senior Scientist and Head Coordinator of the Land Atmosphere Feedback Observatory at the University of Hohenheim, Germany, to present his project titled Rainfall Enhancement Through Modification of Land Cover and Landform Rainland.
So welcome everyone. I'm delighted to present our new project, Rainfall Enhancement Through Modification of Land Cover and Landform. I only have 10 minutes, but I hope I can give you a brief overview and a rationale of the project. If anybody wants more technical details, we can talk about that later. So just a brief overview. I'll mention the rationale for the Rainland project. Why are we modifying the land surface? And then I'll go into more detail about the project itself, our objectives, our methods, and also a little bit about the timeline over the next 3 years and what we hope to achieve. So the rationale for the modifying the land surface is that convective clouds and rainfall are strongly influenced by the land surface, especially in certain weather conditions, such as weakly forced environments. And the land atmosphere system is very complicated. There are many overlapping feedbacks going on. And so here's a schematic of an arid landscape. Now the land surface itself has many characteristics. So we have different kinds of crops, we have sand, we have rocks, and we have the topography, and the land surface itself has its own properties such as albedo or reflectance to shortwave radiation. We have the roughness of the land surface and also things like soil moisture. And these have lots of different feedbacks with the atmosphere, atmospheric processes such as the surface energy balance here, how much heating or cooling, evaporation, and the development of turbulence and the turbulent layer in the atmosphere. It has an effect on the thermodynamic profile, so moisture and temperature. And it can also have an effect on the dynamics of the atmosphere as well, such as horizontal motion and convergence lines. And this can all have an effect or interact with convection initiation and convective processes. So the aim of our project is to exploit our knowledge of these interactions to actually deliberately enhance rainfall by having an impact on the atmosphere by changing those land surface characteristics. So we're proposing two ways of doing this. The first one is land cover modification. So this is more like crops or the color of the surface itself. And there are different ways of doing this, such as with desert plantations, for instance, or black panels. But this one, we're looking specifically at the solar parks, especially taking advantage of the large solar parks which now exist in the UAE. And so we're exploring the use of these areas to create discontinuities in the landscape's radiation balance and surface roughness, and particularly how the contrast between the solar park itself and its surrounding areas. So the processes, basically the overall process, the impact that we're looking at is the surface heating. So you can see here the solar farm is heating because of the lower albedo. And what this does is it creates a low pressure disturbance, particularly at the lee side. So as the sea breeze passes over, the air starts to heat up and you get this low pressure. And this can lead to a wind convergence where the wind draws in and then starts a lifting process. At the same time, we get an increase in turbulence. So turbulent kinetic energy and the boundary layer rises up. If we reach a certain point, so the LCL, then we can get saturation and hopefully precipitation. So these are the main processes. So going back, looking at the sea breeze is very important because the UAE has a strong sea breeze effect, and this is looking at the interaction with the sea breeze is a big part of the project. Just in case anyone would like some evidence, so here is some satellite data from an afternoon time step from 3 of the solar power stations. This is from the International Space Station, eco-stress product. So this is showing the calculated skin temperature, so the surface temperature itself. And then if we compare this with the outside, so take an average and compare to the surrounding 2 kilometers of sand, we can see there's a big temperature difference, yeah? So in some cases up to 8 degrees. So this really is showing that they are really heating up. The second method is land topography modification. So this is modifying existing or even creating new structures such as dunes or hills, could be any kind of structure, in order to deform and force the winds to flow upwards. So here is a hypothetical sand dune here of perhaps 2 to 3 kilometers high. And again, you get different processes, so we get a blocking effect, or we can get a splitting effect of the wind as the sea breeze passes over. And yeah, we can also get lee-side waves dependent on the atmospheric conditions. And so under the right conditions, if we get a strong lifting effect, we also hope to achieve the same effect. So the overarching goals is for us to demonstrate that larger solar PV and topographic structures, which exist at the moment, if larger ones could be used to enhance rainfall in the UAE. So we want to investigate critical processes using the existing structures that we have now, so the solar farms that we have. And using that information gained from observations and modeling, we want to develop predictive indices which are practical and can be used to design effective scenarios, so bigger ones. And then, yeah, we apply that theory in order to simulate and test those larger scale scenarios. So we'll use models to actually see what happens, basically. So we have 3 main working packages and then a synthesis package at the end. So the big part of the project is to combine observations and model simulations together in order to create our predictive indices. And it's really critical that we use both observations and modeling together in this project, because they can give different kinds of information. And then the idea is that we can upscale the model to hypothetical scenarios later. So the observations, these are very important. We plan a 2-month campaign in the summer of 2027. Summer is the most time when we have the best atmospheric conditions for this kind of convection initiation. So we propose to find the sites during 2026 and secure the permissions, and then we plan to spend 1 month at each site, one for the topographic site and one for the solar site. And we'll use a synergy of Doppler and Raman LiDARs, one for to look at the wind field and the dynamics, especially with the sea breeze, and then a Raman temperature and water vapor LiDAR. So these are laser scanners, so light detection and ranging, and these can basically scan in any hemispherical direction, and they will be coordinated together, these scans. So just some example of the scans that we use. So on the left you can see some low-level PPI scans, so scanning at the same time with both LiDARs going over the solar park. We can actually see how the heating is developing. We can see the development of turbulence over, and we can see really what's happening to the air mass as it's advected over the solar park. So we can really see what's happening as the sea breeze passes over in the early afternoon. And then on the right, you can see we can do vertically scanning as well. In fact, we'll have many different scan patterns depending on the weather situation and what we want to really look at. And we could see lots of different processes. So the model simulation's also vital. This is a valuable tool for process understanding. And this is going to allow us to simulate both the existing sizes to compare with the observations, but it also allows us to upscale then to hypothetical scenarios later once we've estimated what kind of scales we actually require. And then we can look at the results. So unlike the last project then when we did this, we're going to go to much higher resolutions this time, down to turbulence scale or large eddy scale, about 100 meters or perhaps even less if we can do it. We plan to configure the model in 2026 to start setting it up, testing it, also model verification as well. And yeah, this is our system that we are using currently, similar to the one you have here. So to put everything together, so everything is planned out, the working package is here, and you can see the deliverables that we've planned also at the end. We also made space for some capacity building activities, so at Khalifa University, but also here as well, where we can involve students and also plan visits to the site and do some workshops as well. This is a very important part of a project. And the outcomes, very simply, is to provide strong evidential support for the effectiveness of this kind of type of rainfall enhancement. And we want to provide the first concrete designs and methods for developing a prototype in the UAE. So we want to actually achieve this within 5 to 10 years. And to do this, we have to cooperate with key stakeholders on technological, economic feasibility, and also environmental impacts as well. So this can only be done in a collaborative way. And yeah, with that, I come to the end. I present the key members of the group, other key members as well. Thank you very much.
Thank you, Dr. Oliver. Now, I would like to ask His Excellency Dr. Abdullah Al-Mandous to come forward to hand the trophies to the awardees. Alia, kindly join us in this memorable moment as well. Dr. Oliver. Doctor. So first, Dr. Michael Dixon. Congratulations, Dr. Michael. Dr. Linda Zur. Dr. Michael. Dr. Michael. Congratulations, Dr. Linda. And Dr. Oliver Brown. Congratulations, Dr. Oliver. Kindly, Your Excellency and Ms. Alia, you can go back to the podium to continue with the Q&A session with the members of the media. Please remember to introduce yourself and your organization before asking your question and to whom you are addressing the question. So the floor is open. Yeah. So we have a question.
Yeah. Good morning, everyone. I would like to ask a question to Dr. Michael. I found your methodology very interesting. I'm just wondering whether it can be applicable to shallow cumulus clouds, because seeding, my understanding is it's typically done at the initial stages of cloud development. So you don't have all all those hydro meteors, and you don't have rain at the time when seeding takes place. So can we extend your methodology to that initial stage of development of the cloud? Because some of the parameters that you list, they are not available at that time. Thank you.
Can you hear me there? I think that, sorry, is this working? Often the seeding target is adjacent to an existing storm of some sort, right? So there may be microphysical signatures that are, yeah, okay, thank you. Yeah, it's possible. It's true that if you have a new storm entirely, you know, the radar signature sometimes only shows up after the pilot has decided that it's a seeding target. But sometimes that's part of a, it's a feeder cell into an existing storm. So I think it's a combination of those two things. It is quite tricky, and it might be that we don't really know the answer to your question, but it may be that we're just seeing typical storms in that area that show seedability, and that we then pick a target which is new that we hope will then behave in a similar way to the existing ones. Okay. So I understand.
Okay, thank you so much.
Thank you, Dr. Michael. Any other questions? Yeah, but can you please first introduce yourself and your organization?
هذا الخياط من جريدة الاتحاد. سؤالي حيكون بالعربي
I think we can just.
هذا الخياط من جريدة الاتحاد. سؤالي حيكون بالعربي لدكتور عليا أو لسعادة دكتور عبد الله المندوس. احنا الجائزة مر 10 سنين على منذ انطلاقها. بدنا نعرف أبرز مخرجات الأبحاث اللي تم الفوز بالجائزة، إذا كان في إلها أي تأثير على الصعيد المحلي أو الدولي فيما يتعلق بمجالات الاستمطار. قد إيه ساهمت في تطوير عمليات الاستمطار، وقد إيه في استخدام لتقنيات الذكاء الاصطناعي فيما يتعلق بعمليات تلقيح السحب وزيادة كميات الهطول المطري. شكراً.
اوكي. شكرا استاذه هاله. طبعا الحين بانتهاء عقد كامل من 2015 لين 2025 احنا اتمنى عامنا العاشر في 2025 هناك الكثير من الانجازات نحن تم انجازها خلال العشر سنوات، بس احنا نعتبرها فقط كبدايه، يعني اتس فيز، ومنها ننطلق لمرحله ثانيه اعمق من المرحله اللي طافت. ممكن ابرز الانجازات اللي تمت انه كان في يعني كفيجرز 100 مقاله علميه طلعت، حوالي 100 مقاله علميه في اهم المجلات العلميه المحكمه عالميا. هناك 10 براءات اختراع تمت خلال هالفتره، واكثر من 120 مشاركه دوليه في المحافل الدوليه. إذا تكلمنا على صعيد المجالات البحثية اللي تم تغطيتها، نحن تم تركيز على مجالات بحثية كثيرة. كانت هناك الكثير من الفجوات البحثية اللي كان لازم نحن في البداية نطرحها ونركز عليها، وأهمها كانت طبعا استخدام الذكاء الاصطناعي خلال هالفترة. من ضمن الإنجازات اللي تمت هناك مادة جديدة تم تصنيعها واثبتت علميا ومن المختبرات، واثبتت حتى في التجارب العمليه خلال عمليات الاستمطار فعاليتها افضل من فعاليات المواد المستخدمه خلال السنوات اللي قبلها بحوالي 3 مرات. هناك طبعا تركيز كبير في الجدوى الاقتصاديه للمواد اللي تستخدم الجديده، في الجدوى الاقتصاديه للمواد بشكل عام اللي نستخدمها، وكيف ممكن نطور منها ونطور من حتى آلية توزيع هالمواد أو استخدامها في العمليات والفعالية، وهذا تم التركيز عليها كثير في خلال هالفترة. طبعا ايضا في خلال هالفتره كان هناك الكثير من الانجازات في الموديلينج وفي الانظمه الموجوده وفي تقنيات جديده في استخدام الانظمه بدون طيار او الطيارات اليو اي فيز. كان هناك الكثير من استخدامها اول شيء في تجربتها في عمليات الاستمطار، وفي ايضا في اخذ القياسات وفي هالامور. خلال هذه 10 سنوات احنا نعتبرها كبدايه، سيتم التركيز اكثر بعمق السنوات الجايه 5 مجالات بحثيه بشكل عام، وهي في تطوير المواد ايضا، تطوير اكثر في وتركيز اكثر في هالمواد، استخدام انظمه جديده لتحسين فعاليات الاستمطار، التدخل المناخي المحدود من خلال تعديل الغطاء الارضي، ومن خلال ايضا طرق اخرى مبتكره، وايضا التركيز على الانظمه الموديلينج، البيانات واستخدامها بشكل عام في المرحله الجايه، واكيد طبعا الذكاء الاصطناعي بشكل كبير جدا.
شكرا مس عليا. Any other questions?
I have a question. I'm Nandini from Khaleej Times. Sorry. My question is that AI models, I mean, this can be answered by either NCM or any of the presenters here. So AI models can predict the seedability in advance by how many hours? And how do these new models compare to, say, traditional models that have been in use over the past so many years?
Can I just ask some clarification there? In terms of hour, are you talking about forecasting hours?
That's right. I'm talking about forecasting hours.
Okay. So with this kind of convective seeding, the forecasts are quite short term, so maybe 30 minutes to 45 minutes in the future. And we're not suggesting that the AI system or the AI technique would necessarily extend the time into the future that you can forecast, but rather that, for example, if you have a consistent bias, you might find that, for example, the coastline or the mountains or some geographical feature causes the forecast to be biased one way or the other, that the AI system could maybe pick that up and correct for those. So it's more a correction in terms of position or in terms of the nature of the storm, the size of the storm at the time, not so much how far into the future it would go.
Thank you.
Thank you, Dr. Mike, for your answer. Any other questions?
I have a question.
Yeah.
Hi, my name is Mariam Saif Al-Bahri. I'm a graduate Earth and Planetary Science student from Khalifa University. My question is for Professor Dr. Volker. It's a very interesting presentation. I understand the type of modeling you intend to test out, but since you mentioned land cover modification, how exactly do you intend to approach this goal? Because you mentioned sand dunes. Yeah, thank you.
I'm sorry, could you repeat your actual question?
So you mentioned land cover modification. How do you intend to approach such goals of modificating the land cover other than vegetation?
Okay. Well, yeah, in this case, for the Rainland project, we want to look at solar farms. So we know from other from many studies that have shown that different types of land use can affect, if you remove a large forest, for instance, this can affect the climate in complex ways, but it's shown that there are effects. So the effect that we're really looking at is the darkening of the land surface and a change in roughness as well in terms of the solar parks, yeah. So we already have solar parks here. Maybe they are not large enough currently. I could be wrong, but they could also be having an effect on convective processes, yeah. But that's what we want to look at. So I guess we are assuming that maybe if we increase the size of the solar parks here, maybe 3 or 4 times, that's just a little bit arbitrary, but something like on that scale, probably from 10 kilometers to 15 kilometers, we think you should start to see a real effect. And this is reflected in the literature. So if you have a solar park now at 7 kilometers wide, for instance, like the Noor Abu Dhabi solar park, maybe we can see effects. So we can see some kind of wind deformation and some heating effects and maybe some increase in turbulence, but maybe it's not large enough to sustain that effect for long enough to create convection initiation. But we want to bridge that link between these small areas and much larger ones by applying simulations, yeah. Observations and simulations. So that's
Thank you so much.
kind of, hope that answers your question.
Thank
It
you
does.
so much,
Thank you.
Dr. Brown. Yes, Mr. Kern.
This is not so much a question. I'm Deonte Blanche. I'm part of the Strategic Directions Committee, and I just want to congratulate the three awardees. Just a general comment, the work that Linda spoke about is really very interesting. She highlighted snowpack augmentation, but if one looks around the world, most of the precipitation that we find, even in liquid form, the ice phase process is involved. So a new glaciogenic seeding material is not just applicable to snowpack augmentation, but it's to rainfall enhancement as well. As a matter of fact, I would imagine that all rain that we get over the UAE has got some ice phase processes involved in them. Just a comment.
Thank you, Dr. Dion. Any other questions? So I think we don't have any further questions. Thank you for your thoughtful ones that you've shared already. And we will now proceed to the press room, which is right next to this room, for one-on-one media interviews. Following the interviews, we invite you to join us for lunch. Once again, thank you all for your participation and for your continued support of the UAE Research Program for Rain Enhancement Science. We wish you all a very pleasant rest of the day. Thank you.
Can we leave